So if you're given an equation, how can you figure out what the concavity is? In other words, where's this function concave down, meaning that water runs off of it? And where's this function concave up, meaning water holds when you pour it in? So, some functions are always concave down or concave up, and some functions change. Some functions are neither, for example, flat functions. But anyways, we want to figure that out by the equation. Remember, we talked about in the last video, it has to do with the second derivative. So let's take a look. So step one, we're going to take the second derivative, and that's going to tell us what's happening to the tangent line, whether it's increasing or decreasing. The first derivative of this function, using the power rule, would be 4x cubed minus 12x squared. The second derivative would be 12x squared minus 24x. So concavity can only change whenever the second derivative equals 0. Kind of like a function can only change from increasing to decreasing whenever the first derivative equals 0. So there's a relationship there. So step 2 is going to be to determine whether the second derivative equals 0. Because if the second derivative goes from positive or negative to positive, that's the only way it can change concavity, and of course that can only be at 0. Remember, if the second derivative is negative, it's concave down, positive, concave up. Let's set this equation equal to 0, pull out a 12x. Now we can see that x is going to be 0 or x is going to be equal to 2. Okay, so what do we do with this? Well, we're going to make a chart just like we did with increasing, decreasing, except it's going to be a second derivative chart. Now before we do that, I do want to mention, just like a critical point exists when the first derivative equals 0 or it doesn't exist. Well, a critical value for the second derivative is also where the second derivative equals 0 or where it doesn't exist. So before you draw your chart, make sure you determine where the second derivative doesn't exist. Now, in this case, the second derivative is a polynomial, so it exists everywhere. But let's say you had a fraction for the second derivative. You would want to set the bottom equal to 0 and solve for x to see where the second derivative doesn't equal to 0, because that could also be an inflection point, which of course is where it changes concavity. We'll talk about inflection in the upcoming lesson. So step 4, we're going to determine our intervals from those x values, just like we determine intervals from increasing, decreasing. We have two x values here, 0 to 2. Remember, you have to start at negative infinity and go to your first one, 0. Then your middle one is going to be from 0 to 2. And your last interval is going to be from 2 to infinity. So remember, if you have two critical values for your second derivative, you're going to have 3 total intervals. So this will be negative infinity to 0, 0 to 2, 2 to infinity. Those will be my intervals for step 4. Now we're going to draw our chart for step 5, and I will explain this chart. There's a lot going on here. In the first column, you're going to put your interval, just like you did for your increasing, decreasing intervals, but this is the second derivative. Next, you're going to plug in test values like you did before. Negative 1 is in between negative infinity and 0. 1 is in between 0 and 2. And 3 is in between 2 and infinity. Now we're going to plug those into the second derivative, and that's because that's going to tell us whether it's concave up or concave down. So here's our second derivative. We're going to plug these test values into that second derivative. So we're going to plug in negative 1. We're going to plug in 1 into the second derivative, and we're going to plug in 3. Now our next column, we're going to write out the value we get when we plug those test values in. So when we plugged in negative 1 here, we got 36. When we plugged in 1, we got negative 12 into the second derivative, and when we plugged in 3, we got 36. So here's our next column. Again, just like increasing, decreasing, for concavity, we're just worried about whether or not these numbers are positive or negative. This number is positive, so I'm going to put a positive in this column. This one's negative, so I'm going to put a negative, and this one's positive, so I'm going to put a positive. And what does this mean in terms of concavity? Remember, when the second derivative is positive, it's going to be concave up. And that's because the slopes of the tangent line are increasing. Okay, so it's going to be more like a U shape, and therefore we're going to put up for positive. Here we got negative for this interval, 0 to 2, so it's going to be concave down on this interval, 0 to 2. And we plugged in 3, we got positive, so it's going to be concave up from 2 to infinity. So concave up from negative infinity to 0, down from 0 to 2, and up from 2 to infinity. And again, that's based on the sign we got when we plug these test values into the second derivative. Let's give a verbal explanation here. The function is concave down on the interval 0 to 2 because the second derivative is always negative on that interval. So make sure when you explain, you give a reason. Then the function is concave up on the interval negative infinity to 0 and 2 to infinity because the second derivative is always positive on those intervals. Again, make sure that you give a reason for that, okay? And of course, these intervals came from those test values you plugged in, which at those particular points, they're either going to be 0 or undefined. So let's take a look at the graph of this function. All right, here's our graph, x to the fourth minus 4x cubed. We can see that right off the bat when we start on the function, it is negative, the slope of the tangent line, okay? But as we go from left to right, it's actually increasing. Okay, so the function's actually increasing from negative infinity all the way up. The tangent line will keep increasing until about right there at 0, okay? Then the slope of the tangent line is going to start to go down again, meaning if you pour water on this graph, it will actually run off. Okay, but you can see it's going to decrease, 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 but at some point right there, you'll see the tangent line, the slope will start to increase, and the second derivative will be positive again. And it's going to do that from 2 to infinity. The tangent line is going to increase in forever as x to the fourth minus 4x cubed approaches infinity. So this is a visual way of understanding the change in concavity as the slope of the tangent line increases, then it decreases, then it increases again. That's it for this example of finding the intervals of concavity. If you have any other questions about it, let me know.